Hi. So today we're going to talk about, we're still in topic number 3. We're talking about plane stress and plane strain. So let's think about this concept. What is plane stress and what is plane strain? To understand this, let me grab two things. So let me grab a piece of paper, okay? And I want you to think about this. I have this piece of paper, I'm holding it, and I'm going to apply a load in the middle, right? So when I apply the load in the middle, I'm holding this paper and apply this load in the middle, you can see that applying certain amount of load, there is a deflection involved with it, right? The purpose of that deflection is because there's no resistance to that deflection. There's not enough energy absorption. So therefore, what's happening is we call it plane stress because it doesn't have the capability to resist loads in this direction. The load applied keeps on going. Okay, so think about this case. So think about this case. So I'm saying it's so thin that if it is the case of pin, for example, and apply a load there, what this is really doing is deflecting like this. So therefore, if I'm trying to see how much load this is resisting here, will be very close to, basically there's no load resistance. Now, on the other hand, I wanted to consider a case maybe like this. A case like this. Consider the course textbook, right? So now if I take the same amount of load and apply it in the middle, you can see that I'm applying that load and there is no deformation here. The reason behind there's no deformation is it has enough energy absorption. So when my load goes in here, my load is absorbed by all the energy and doesn't let this be deformed. Okay, so there is an action reaction to this. Because there's action reaction, then my loads kind of cancel out in that direction, and there's not enough to actually to have a deflection in this direction for the same amount of load. So this second case that I just explained, you could consider the same problem, uh, same problem. Consider 100 pounds, okay? Just to make sure the problem is completely identical. So now I did the same problem, okay? And apply the load, and my deformation basically remains the same. There's no deformation. And the thing here is this is very thin, this is very thick. In this case, since it did not deform, that means that it has some energy resistance in here that's actually opposing this load. Okay, and all this that's happening there, this is basically nothing else than if this is the z direction, you're saying that your sigma zz is bigger than 0. Here, I'm saying that this load here is very close to 0. There's almost none. So we can say that sigma zz is almost equal to 0. Okay, so in this case here is called plane stress, and this is called plane strain. Okay, and as I mentioned, in this case, this is almost 0, and this is bigger than 0. Okay, and this is true because this is z. Okay, if this was y, then this would be sigma yy. If this was x, it would be sigma xx. It's the direction perpendicular where my loads are actually acting on. Okay, so if that was the case, In such a case, what is true in the case of plane stress, this plane stress is very common in most of our problems, and we're going to see this very, very often. For plane stress, what is true is sigma, your third stress invariant, is equal to 0. However, the opposite is not true. So if sigma 33 is 0, we cannot say it is plane stress. Okay? So if we use our characteristic equation that we talked about in the first class, in the topic of stresses, it looks something like this. Okay? So if this guy over here is 0 now, if that goes to 0, then your equation becomes as follows. There's a 2 there, sorry. Lambda squared 2 lambda is equal to 0. Or I can factor this lambda out, and you have basically a quadratic equation that's very easy to solve, and you know the solution for that. Okay? And you know that immediately one of the roots will be lambda is equal to 0, and the other root is going to come from here. And that root is going to be sigma 1, comma, sigma 2. I typically use that sigma 3, and that would be equal to sigma average plus minus sigma difference squared plus tau xy squared. Okay? Where sigma average is nothing else than sigma xx plus sigma yy divided by 2, and sigma difference is the difference of this. This is if we are working the case where your cross section looks like this, x and y. Okay, your z goes inboard, outboard of the plane. That's your z that goes inside and goes outboard. Okay, if that was the case, and then in that particular case, you still have to do the same as usual. Sigma 1 would be maximum of lambda 1, lambda 2, lambda 3. Sigma 3 would be the smallest of that as well, lambda 1, lambda 2, lambda 3. And your maximum shear will be the same, sigma 1 minus sigma 3 divided by 2. Okay? So to better understand this, we can do a couple of examples, and we'll leave that for the next video.